एसी नहीं ऑन होगा? ऑन होगा। ओ अच्छा 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 अच्छा, थैंक यू नहीं बोल। Oh, अच्छा. Navin, also one thing. We have won this journal club, String Journal Club on this Friday.
Oh, okay, I got the email.
Yeah, so you got
Okay.
it. Achha, achha.
You want Zoom link?
Yeah, Zoom link.
How you this is hybrid or
Hybrid.
hybrid?
Yeah, hybrid.
Some people will join online.
Yeah, some people
Okay,
journal.
I'll share you the Zoom.
Okay, okay, thanks. Yeah, thanks a lot. Thank you.
Hi everyone, welcome back to ICTS String seminar series. So for this week, we are happy to have Sayantani Bhattacharya from NISER. Okay, so over to you, Sayantani.
Hello.
You can.
Am I audible?
Yes.
Okay, so thank you for giving me the opportunity to talk here. So I'm sharing my screen. So is it visible? Hello.
Yeah, it is.
Okay. So let me start. The title of my talk is zeroth law in higher derivative theories of gravity.
Hello.
Hello, yes.
Possible to make this notebook landscape?
Okay, no. Like this?
Yeah, that's better.
Okay, shall I, should I write in a bigger font?
No, this is good.
This is okay. Let me make it a bit. So, so the plan of my talk is as follows. So first I'll explain what do we mean by zeroth law. The second, I'll come to the motivation. And the motivation will have two parts. One is a very small, like thermodynamics and zeroth law is expected to be followed like that. And the second part is one is, I would say, something thermodynamic of black holes, thermodynamics of black holes and things. And the second part, which is also related to the thermodynamics of black holes, but is more elaborate, is a technical motivation. I'll call it. And it will be a large part of the talk. And here I'll say that the zeroth law is actually used in the proof of second law and also probably the first law. So zeroth law is needed for the proof of second law and first law also, but which I will not elaborate. So we need zeroth law to be satisfied in the context of black hole. In the context of black. And the third part would be the proof itself. In this technical motivation part, I'll develop some terminologies which I'll be used for the proof. And the fourth is digital. We start with the first part. What do we mean by zeroth law? So we'll be dealing with stationary black hole. Stationary black hole. And we'll assume it will have a killing horizon. So in our description, horizon is a null surface. And the horizon generator is proportional to the one bulk killing vector. This is the first property. It's a null normal to the horizon. Proportional to a bulk killing vector. Let's call it del tau. So tau is the killing coordinate. This will be our system. Now, in this kind of a black hole, this is the black hole, stationary black hole. The metric could always be written in this form. Give a name to this vector. Del tau and like psi. This is the killing vector is called psi. In this particular coordinate, it is del tau. We've chosen the coordinate to be tau. Metric could always be written in the form ds square 2 d tau d rho minus rho x tilde, which is a function of rho and the other spatial coordinate d tau square is 2 rho, which is also a function of rho and other spatial coordinate d tau dyi plus hij. Hij is also a function of the other coordinate. Nothing depends on tau because tau is the killing coordinate. So it's an isometry direct, global isometry direction. So nothing depends on tau. So this is the form of the stationary black hole. And here rho equal to 0 is the horizon. then the temperature of such black hole is given by the surface gravity, and the formula is this. The formula which is given as minus of D is the covariant derivative with respect to the full metric, psi is the killing vector. Field we have already defined in this coordinate dictate out. And if I evaluate this particular formula, so this temperature is the temperature that appears in the first law in a generic situation. And if I evaluate this kappa in this metric, which any black hole could be written in this form, and evaluate this kappa on this metric, kappa will turn out to be del kappa is equal to half x tilde at rho equal to 0. And the zeroth law says, like what do we mean by zeroth law? It's the following, that del yi of kappa, which is also equal to del in our coordinate del y of x tilde evaluated at rho equal to 0 is equal to 0. In other words, kappa doesn't depend on other yi direction. Or kappa is constant on the horizon, which is rho equal to 0. So this is what we mean by zeroth law operationally. So just to summarize, any stationary metric could be written in this form, where tau is the killing coordinate, and therefore nothing depends on tau, none of the metric functions. Rho equal to 0 is the horizon. We have chosen the origin of the horizon on the rho, origin of the rho coordinate on the horizon. And if this is the general formula for temperature on any black hole, this is the temperature that usually appears on the first law. And this temperature, if we evaluate on this metric, it will turn out to be this x tilde, this function, the coefficient of d tau square. Oh, sorry, there is x tilde. And then the zeroth law means this temperature, this kappa or this x tilde is independent of rest of the y coordinates. So this is what we would like to show in this talk for any higher derivative theories. Is the question, the statement clear?
Yeah, Sayantani, I have a question.
Yes, sir.
Yeah, which is that normally when you prove first law, unless the zeroth law is true, you cannot prove first law, presumably, right?
Yes. Even that is true for second law as well. Like
Yeah,
second
but
law
let's
would have
let's just take the first law.
Hmm.
So when you define world entropy, how exactly it is defined without, if you don't have zeroth law already?
So that's why I'm not even defining. So what I'll show that
The world defines some entropy, right?
world has defined some entropy, and world has said that suppose zeroth law is true, and then this is the world entropy. If zeroth law is true, kappa is constant everywhere, this kappa, and then he can write the first law for world in terms of world entropy.
So he assumes zeroth law and then he defines the world.
Everywhere zeroth law is assumed.
I see. Okay. Thank you.
The world's case, I'm not saying, it's written somewhere in the paper that let's assume zeroth law is true. And then after that, zeroth law has been proved for different higher derivative theories. For example, in Lovelock theories, it has been proved. Then some other theory, it has been, so different particular higher derivative theory, it has been proved. So, but what we are trying to do for any higher derivative theory, recursively will prove this. So I think zeroth law first has to be proved, then the first law comes, then second law. Okay. Like this should be the sequence.
Thank you.
So I have a question. What's the difference between y tilde and y?
y, oh, it's not y tilde. This is yi vector. So it's a vector sign I'm using.
Okay, so
It's
when
this one.
so the zeroth law equation, that y bar or y tilde, that's not a.
Oh,
That's
that's just typo. That's just del yi. This is it. So I might write yi or just y with a vector sign. That's it. This thing is equal to y vector. Sometimes I might use this notation, or I'll explicitly write yi. This is okay.
Hello.
Ah, yes.
So I wanted to ask a question. So here we are assuming that the horizon is some connected surface. Is that right?
Here we are assuming, I think we are assuming the horizon is some connect. I am not sure how explicitly we have used it because all the analysis are very local at every point. But in like I never thought of disconnected surface. Maybe the same proof could be extended to disconnected surface, but I have not thought about it. Let's say it's connected. And also I'm not using any matter field at the moment. I'll assume there is no matter field, though I think the proof could be easily extended also with matter field, but for simplicity, I'll assume it's not there. Okay, so this is the statement of this is what we mean by zeroth law. So now I'll come to the second part, the motivation. The first motivation, as I asked, is already discussed. It's like we should have zeroth law to have the first law. Like if temperature is not defined, if temperature of the black hole is not defined, there's no question of having a first law. Temperature not defined. Like if it depends on yi, then it's not a constant temperature even on an equilibrium situation. So not defined, no first law, no second law. Or second law. So zeroth law is that's why important because we need to have a constant temperature to have black hole thermodynamics working properly. Even for higher derivative theory, we need to know to have constant temperature in equilibrium black holes. We need to associate constant temperature with equilibrium black holes. So this is the first part of the motivation. But the second part is a bit technical, and that will also lay down the techniques that will be used for the proof. So therefore, we'll come to the second part of the motivation. First and second law. So this the first law. Okay, I'll not give the description of first law and second, like the proof of first law and second law. So that's not the topic. So I'll not prove first law and second law. I'll just show where this zeroth law has been used. This is the physical process version of the first law I'm talking about. Where the zeroth law will enter. That's the only part that I'll describe here. So suppose, so to show that I'll assume, suppose zeroth law is true. So assume zeroth law is true. Then how it will lead to the other two laws. Assume zeroth law is true. So the above metric, the metric that I just now I wrote, which is of this form. Low X tilde. So I'm not writing the arguments. Square. So we have assumed zeroth law to be true. So which means del I of X tilde at rho equal to 0 equal to 0. So you can write X tilde as follows. X tilde is equal to some constant C plus rho times Z. It is again a function of rho y. So at rho equal to 0, the value of X tilde I have taken it to be C, which is constant, like independent of both T, tau, and Y and everything. If I substitute it, so that then the metric will, this term, the d tau square term will be just this. Minus rho C d tau square, rho square Z. So I've taken out this constant piece outside. Now, once this is true and C is constant, I can do a coordinate transformation. Now, a particular coordinate. So now, tau is a parameter along the null generator of the horizon, but it's not the affine parameter. Not the affine parameter. We can affinely parameterize. And finally parameterize the horizon. You can affinely parameterize the horizon anyway, but if C is constant, this reparameterization becomes very simple and something good happens after that. So this reparameterization where tau will go along the affine parameter of the horizon generator, could be done in this way. So we'll define a new coordinate V, which is the affine parameter along the horizon. By C to the by 2 tau, and R coordinate accordingly redefined to the minus C by 2 tau. And yi is remaining, so yi is, I'll call them x's, but they remain there. So this is the coordinate transformation where V is a affine parameter, and this coordinate transformation will take it to the affine parameterized form. If I substitute it here using C equal to constant, the dA square metric now will take in this coordinate this form. Now X. I'll just write like this. And the second thing, all of them, these metric functions, I call them metric functions. Z, omega I, and hij will be functions of R times V and X. Because if I look at it, we can see that R times V is actually C by 2 R times V is actually rho. So it depends on rho, but rho in this new coordinate will be a function of R times V. So that's true for stationary metric. So in this coordinate, the key point is this R times V, and rest of the metric takes this following form. And it has and the tau symmetry, the tau translation symmetry, tau was this killing direction, so it would translate reduced to something called boost symmetry. In this new coordinate becomes boost symmetry. The name, but the symmetry is like this: V going to lambda times V, lambda constant, and R going to R by lambda. You see, under this transformation, the metric is just invariant. It's a product of R times V, so it doesn't change, so it remains invariant under this transformation. And everywhere where is dV square, there is an R square. If there is a dV, there is an explicit R. So metric remains invariant, and as it should be, because this is the tau transformation basically. So now this, and just to emphasize that all of this transformation and the metric becoming so simple, like we can always transform to an affine parametrization, like we can always affinely parameterize the horizon and can do the coordinate transformation. But in that coordinate transformation, it will not happen that the metric, this thing is function of R times V. It will depend on yi also if C is not constant. Because C is constant, it becomes just a function of R times V, and everything becomes a manifest, like everything has a manifest boost symmetry. And that will be heavily used to construct the first law and second law, this, and even an entropy current on the horizon using this boost symmetry and weight. So here this C equal to constant is crucially used in these proofs, for this coordinate transformation. So C constant has been crucially used. This coordinate transformation to used so that is used to cast the metric in such a simple form. Now I'll talk of something called boost weight. You can associate a boost weight with any covariant tensor component. So T is some covariant tensor, any covariant tensor, and it has some number of V indices in this coordinate system. We're writing everything in this coordinate system now. Some number of R indices, let's say M of V indices, some N number of R indices, and then I1, IK, K of K, this kind of spatial indices. They could be randomly distributed. It's not needed that all the V's are together, R's are together, I's are together. See, this is a coordinate, this is a covariant tensor component. And this is just a coordinate transformation which transforms this boost symmetry is just a coordinate transformation which involves only V and lambda, lambda being constant. We can clearly see that under this boost transformation, this will go. So if I do that scaling, D going to lambda V and R going to R by lambda, this one will go lambda to the M, then lambda to the minus N, then T, then new coordinate T. So any covariant tensor component with some number of V indices, some number of R indices, and some number of I in the spatial indices, under this boost transformation, this one, how will it transform? It's very simple. It's just given the number of V indices times lambda to the m, and the number of R indices will come with a minus n, depending on how I am taking my lambda, 1 upon lambda. So it entirely depends on how many number of, what is the number of lower V indices and number of lower R indices. So we'll define boost weight of any tensor component. This part of it technical, some definition is needed as number of lower V indices minus number of lower R indices. Now this, why I'm defining this boost weight, using this boost weight, we can classify terms. So using boost weight, now using boost weight, we could classify terms depending on, like we can classify terms in terms of how close they are to stationarity, in terms of how close they are to stationarity. So boost weight could be used as a measure of departure from stationarity. So I'll come boost weight could be used as a measure departure from stationarity, and both first and second law, particularly second law, and now both first and second law requires us to go away from a given equilibrium situation to another equilibrium situation. So it needs a dynamics. You start from some equilibrium, then you landed in another equilibrium, and there are relations between their entropy and how it is increasing and so on. So both first and second law require some dynamics. And the boost weight, both first and second law, requires some dynamics. And boost weight used to segregate terms or classify terms. And boost weight is used to characterize this dynamics, by proving these laws. Y indices do not transform under the boost weight. P, R, and I. So for I's don't transform. So boost weight is just a scaling. The metric is invariant under this particular scaling. R goes to R by lambda, V going to lambda V. The lambdas will get cancelled. Everywhere it is in that kind of a combination. Y's are not transformed. So that's why boost weight just figures out how many R's are there, how many V's are there.
Hello?
Yes.
You said that boost weight characterizes departure from stationarity. Means stationarity, yes. The tensor we are talking about.
Sorry?
When you say the boost weight characterize the departure from stationarity.
Yes.
What do you mean by, stationary of what?
Now, stationarity means stationary black holes. Like if something is not a stationary black hole, how looking at a particular tensor component and evaluating it, we can figure out. I'll come to this. This I'll describe in detail.
Hello?
This is one of the key part of the proof of this particular thing. So how it differs. But here I'm giving a bit of technical thing. I'm giving some general motivation that why boost-weight is necessary for first and second law. But I'm coming to this particular point why it is a departure from stationarity. And this is what I'm just going to talk now. Okay. Now consider departure from stationarity.
Hi, correct. I had a question.
Yes.
When you depart from stationarity, won't the boost symmetry be broken?
Yeah, it will be broken, and I can figure out how much it is broken, and that's how I'll measure the departure from stationarity. Basically, I'll check whether the boost symmetry is there or not, in some sense, but in a quantifying way.
I see. Thanks.
Just general question: how much time I have for this?
Yeah, you can maybe 4:15.
4:15. Okay, thank you. Boost weight and departure from stationarity. Now consider a tensor component. Evaluate it on the horizon. Which is at rho equal to 0. And let's say the metric is not stationary. So we could always write the metric in this form, even if it is not stationary. dBdxi. It has come from the stationary part also, but you can independently show that any metric with a horizon and v being the affine parameter along the horizon generator, you can write it in this form. But now the only thing is that z omega I. So z will not be function of r times v, but now boost weight is no longer, boost symmetry is no longer a symmetry, it's not stationary. So therefore z will be function of r, v and xi separately. Similarly, omega I will be function of r, v and xi separately. That's the difference from if it is not stationary. So if they are separately r and function of r and v is no longer stationary because it's not and then no longer there is boost symmetry. It's not invariant anymore because r times v is invariant. If r and v separately appearing individually in a different way, it's not invariant. So this is the general structure for a non-stationary metric. And if it is stationary, this r and v will always appear in a product form. Non-stationary. So now in this metric, if you apply boost transformation, those z and omega I and hij independently are not covariant tensor under the full bulk space-time. You could see that the boost transformation, the r will change and the v will change, and they will cancel each other. And therefore, z will not have any overall factor. The arguments of z will change, and that will break the boost symmetry. But the overall z will not change. So z, omega I, and hij, even in a non-stationary situation, will not have any boost weight. Weight. What do I mean by that? That will not be multiplied by any overall scaling. Will not have any overall scaling under boost transformation. Even in the non-stationary situation. So if I have a covariant tensor, following property that if it is constructed only out of metric component, constructed only out of the metric, like Riemann tensor, Ricci tensors, or some such thing, which are constructed covariant tensors and constructed only out of metric, and have some boost weight. And third, evaluated on the horizon at r equal to 0, must have the following structure. Let's call it W. Some number of derivations.
Anthony, now we are talking about covariant tensor constructed out of the metric of the original background.
Of this
Boost invariant metric.
Boost invariant. Boost invariant, but not this one.
Oh, I see.
Like
They can have
non-stationary
tendency.
metric.
Okay, okay.
Yes. I want to constrain the structure of the component, this particular covariant tensor component, in terms of Z, omega I, and Hij using boost weight. So it's how its structure will be constrained. Must have the following structure.
But eventually you want to prove the first law for the original metric, right? For the stationary metric, or no?
Eventually, for the stationary metric, yes. I want to prove it for the stationary metric.
Okay.
I see that some particular kind of tensor component will always vanish on the stationary metric. So that's what I want to show.
Okay.
That component will appear in the equation of motion at every order. So that will be
okay.
So they will have some number of del V, some number of del R. Then some number of del I, either acting on these metric functions, this X, omega I, and Z, not X's, Z, omega I, and Hij, and product of such terms. It need not be that all of them are acting on one thing and their products. So this is the only structure possible. Some derivatives acting, there is no explicit factor of R, and if you evaluate any tensor component, the only structure possible, and product of systems, But the boost to it gives something more, product of such terms. So if I evaluate a covariant tensor component on a metric like this, and evaluate it at R equal to 0, so no explicit R factors can appear. So only possibility is that some number of del V, some number of del R, some number of del I is acting on these functions and their product. They're distributed different way and their product. The derivatives are also distributed randomly. So this is the only possible structure, but it has boost to it W. And you see this under the boost transformation, under this scaling, the Z does not transform, Wi does not transform, Hij does not transform, the del I does not transform. Only del V and del R transforms. So if it has boost to it W, that means under boost transformation, it has to have the whole tensor component should have an overall factor of lambda omega that must be given by these del V's and del R. So boost weight W and W must be equal to M minus N, because del V's will give lambda to the M, del R's will give lambda to the minus N, and the overall lambda factor is W. So therefore W must be M minus N. Is this statement clear? The boost weight, so for a covariant tensor component evaluated on the horizon and constructed only out of metric, the boost weight must be equal to the number of del V's minus the number of del R's.
Z and H appeared with some R factor, right?
No, but you are evaluating on the horizon, so all R factors are vanished. So horizon is at R equal to 0. Is that okay?
Yeah, thanks.
And you are not allowing any matter fields, or is this automatically included somehow?
At the moment, I'm not allowing. Actually, the recently Nilay and they have done another analysis where they have seen that for matter field also this will happen. So if you include that, everything will go through. But at the moment, I'm not allowing.
Okay.
Matter field, there are issues like if you have a gauge field, you have to gauge fix it. Like you can choose a gauge which breaks everything. So all those things have to be subtly set, but could be set. Like there is no obstruction to it. If all those things are taken care of, even in matter field, this will work.
But you cannot work in the gauge invariant form because this is classical analysis, right? You
They
just use
have
that
worked,
menu and things like that.
with that also they have worked out only for abelian thing. It could be done for gauge invariant ways as well, I think.
Okay, thank you.
So we have seen that the non-zero value of omega gives the non-stationarity condition, but does it also quantify that by how much it differs from stationarity?
It quantifies in some way, though I'll not be using it. If okay, let me just finish this thing, then I'll quickly mention that. That is required for even the dynamics and second law. But for this proof, it is not required. Only this much is required, that non-zero is non-stationarity. So for a covariant tensor component, component evaluated on R equal to 0, constructed out of the metric, the boost rate W equal to number of del V's minus the number of del R's in the final. Now suppose we have a, now consider, it's already mentioned, but let me again consider a tensor component with positive boost rate. W greater than 0, which means number of del V's is greater than number of d. Now evaluate such a tensor component on a stationary metric.
So I have a question about the definition of boost weight. If you take a linear combination of two tensor component which have boost weight, can we define the boost weight of the combined object? Because it might be possible that we can, it can be easily possible that we can take a linear combination of two objects which have different weights.
You can have linear combination of two objects with different weights. Then you cannot define a boost weight for that object.
So the form you have written down is not the most general form. The most general form would be the
It's for a given component. It's not the full tensor. A tensor you take, you take a tensor, you take a particular component of it, you evaluate it on the metric. This is the only structure that will come out.
Okay. Okay.
And for that structure, this is. And if the overall, see, you are saying that there are many such structures will come out. So if an overall tensor component has a given boost to it, all the structures that will come out will have the same boost to it, right? Because it's well defined. So for example, you are taking TVV. So it must have the structure of the from del V acting on something, then del V acting on something, or del V square acting on something, or del V4 del R square acting on something, or something like this. But all of them will have two extra twos because the overall thing, this has boost to it 2. So every term you will have should have boost to it 2.
Okay.
Okay. Sayantani, so I mean, do you need to actually express in terms of derivatives, or if you just look at a particular tensor and you know which component you are looking at, suppose you write everything in lower components, isn't that good enough to determine the boost to it?
That's good enough to determine the boost to it. But now I'll also say something for which derivatives. So it's like if you have boost, you know the lower components, you count them, you know what is the boost to it. Then further, you know if this is the boost to it, and then you evaluate it on the horizon. The boost to it is actually number of del V's minus number of del R's. And because of that, something will happen. Because of that, the positive boost to it tensor component will vanish on R equal to 0 on stationary solution.
I see. Okay.
Now number of del V's, now to speed up a bit. Now evaluate this tensor component on stationary metric. So we have del V, some number n, del R, some number n, then del I in any number, and acting on some metric component. So this is the structure, the basic structure. But now this metric component is function of R times V because it is stationary, and Y or X. So its arguments are R times V. So every time I divide, like if I take del V's, every time I take a del V, a factor of R will come out. And those factors of R can be taken care of by del R's. But if number of del V's are more, you will have more factors of R than del R's. And therefore at R equal to 0, it will vanish. So therefore on stationary metric, any tensor component with positive boost to it will vanish. Is this argument okay? Just to repeat, every time I'm acting with del V, one factor of R is coming out. It is R times V, the arguments are. Those factors of R could be killed by this del R, but if the number of del R's is less than number of del V's, some factors of R will remain. And if I set R equal to 0 at the horizon, it will vanish. So on stationary metric, on the horizon, with W greater than 0 will vanish. Now, this is the thing that I'll use to prove the zeroth law. Nothing more is needed from here. But this is what has been used to prove first and second law as well, because this means a boost to it positive terms are away from the stationarity, are always dynamical. And product of two terms, which has boost to it positive, is quadratic in the amplitude of the dynamics. So any term, and this is how we quantify the departure from any term with W greater than 0 is dynamical. Product of two terms with both with W greater than 0. It's quadratic and so on. This will not use for the 0th order thing, but this is what in response to there's a question that how can I quantify? It's quadratic in the amplitude of the dynamics. Because first term is dynamical, second term is also dynamical, so it must be quadratic if are doing any amplitude expansion in dynamics. And this is what is used to prove the first law and second law. So this is the quantification, and this quantification of the departure from dynamics which is used.
So dynamical means what exactly? Is that it?
Dynamical means, okay, if you want to know operationally, in this case, it's not a product of R times V. R and V are appearing independently.
Okay.
So this is the operational definition.
But this is true also for W less than 0 terms.
The dynamical, okay, which just a minute, you want to know what this dynamical means. Okay.
Meaning, why are you calling them dynamical? Okay, I mean, you can of course define it. Yeah. But
I mean that any term with W greater than 0 is dynamical, means they are non-zero only when dynamics is on. That's what I mean.
I see. Okay.
It's non-zero only with, that's what I mean by this dynamical.
Okay.
Only when and departure from dynamics used for both first law and second law proof. This is the first law physical process version, I should say. In world's proof, it might have been used, but I have not been able to understand it. There's another kind of proof for first law, which is physical process version, where this has been used. Second law. Both first and second law. But I will not be using here for this talk. Now I'll come to the proof. So this much is for motivation. And this whole of this analysis, this boost to it, and everything is possible, because we could take that the first metric to the second affinely parameterized form. So this two, if you remember, this particular metric we could reach from this metric, the one that we have started from this one. And that is possible provided C is constant. If C is not constant, you could still go to the affinely parameterized form, but this equilibrium will not have product of RV, stationary solution will not have product of RV, then this statement will not be true, and this quantification will not be true. So it's not being said that it's just not, like it has been heavily used everywhere. So C is constant, it's very much used everywhere, the temperature being constant in all the proof, and using the same technique. So now I'll come to the proof.
Hello, hi Sayantani. So I am just confused about a small point. When you say dynamical, you're saying that the only departure is in those metric functions, instead of being functions of R times V, they are individually functions of R and V. But is that the only, I mean, is that a complete parameterization of all departures from stationarity?
I think so, because if you start with any, as long as you have a horizon, if you assume, you can construct this coordinate system. So you can always choose a gauge where this metric will come to this form, where dV is the null affine parameter along the null generators of the horizon.
Okay.
So you can come to this form, then the most general case, omega I, Z, and Hij, these are the functions. All of them will be function of all R, V, and Xi. So this is the most general metric possible. Then in equilibrium, there will be product of RV. And that part is not clear from this description if you start from this way, but that part will be clear because this product of RV is basically this del tau translation.
Right.
So I think it is even more, this statement is more constraining, saying that equilibrium, it will be product of RV and nothing else is possible. But in the most general situation, it will be function of RV and Xi. That I think is the most general situation.
That it will. Okay. Yeah, I guess, yeah, it has the right number of, yeah, I guess you can always bring it to this form and then this, yeah.
Okay, now I'll come to the proof. Proof will be done in a method of, okay, the proof, what are the assumptions? The assumptions for this proof, it's not the most general proof, I must say. Is that the Lagrangian is of this form. The full Lagrangian is alpha to the 2k L k plus 2 k equal to 0 onwards, any value, where k equal to 0 corresponds to Einstein. Gravity. Derivative gravity. So Lagrangian is this form, and the assumptions are this, that alpha is a small parameter. Higher derivative coupling is a small parameter. Makes sense to expand in powers of alpha. And the solution would also be expanded and also be constructed perturbatively. G AB, which is the solution to Einstein equation, this one, plus alpha square G2AB plus alpha to the 4 G4AB. And this is the perturbative construction of solution. Like we can first solve for G0AB, then use that to solve for G2AB and use that to solve for G4AB. And order by order, we could do the solution. And this makes sense. Alpha is such a parameter where this makes sense. So this is the basic assumption. So whole of the metric and everything has a very smooth limit to alpha equal to 0 or Einstein gravity. So higher derivative theory admits a smooth theory, higher derivative theory and the solution. On the BH solution we are considering admits a smooth limit. To Einstein. This is the key assumption. Okay, then the solution, the proof will be using the method of induction. Assume it, we'll first show it for 0 known, but we'll first state it for Einstein gravity, which is well known, like Einstein gravity temperature is constant. So everything makes sense in black hole thermodynamics. And then we'll assume that it is true for alpha to the 2m order. And if it is true up to alpha to the 2m order, the temperature is constant up to alpha to the 2m order. It will be constant in alpha to the 2m plus 2 order. So that is the proof. That's how I. So first, alpha to the 0 order proof. Einstein gravity. Here we need an exact statement. So here, if we look at E tau I component, so starting with this metric, dx square is equal to d tau d rho, the original one where C is explicit. So this is the metric, and since metric admits an expansion, everything admits an expansion. So C is also C0 plus alpha squared, C2 plus alpha to the 4, C4, and so on. Everything has similar kind of things, Z0. All other functions also it is true. Now for alpha to the 0 order, if we look at the equation, and the same will be true for equation of motion. If I look at the equation of motion into 0, this is basically Einstein tensor. If you explicitly evaluate it on the horizon on this metric, it will turn out to be this. On the 0, it will turn out to be half del I of C0. By explicit evaluation. Now, E tau I is 0 everywhere. We are not considering any matter field. So half del I C0 is 0 from equation of motion. So therefore, C0 is constant. This is the proof at 0th order. Now let's assume it is true at. Assume the statement is true up to order alpha to the 2m. Then I'll try to show that if it is true up to order alpha to the 2m, it's true at order alpha to the 2m plus 2. Everything is square order. Alpha is a length scale. So now, just one notation to simplify the writing. Let's define this thing. Any question? A finite truncation operator, alpha to the 2k e. V2k plus 12. E is the equation of motion. If you were. So similarly, G A may be is k equal to 0 to m alpha to the 2k G k. Now the equation is true up to alpha to the 2m. So which means if I evaluate, so what does this statement mean here? So if MAB is evaluated on GMAB, the answer would be of, like up to alpha to the 2m, it solves the equation. So answer is of alpha to the 2m plus 2, order alpha to the 2m plus 2. Because GMAB solves ENAB up to order alpha to the 2m, which we have assumed. So this statement means this. So ENAB may be evaluated on GMAB. Now the next thing is at order alpha to the 2m plus 2, if we want to solve it, up to order alpha to the 2m, everything is solved. The unknown is, the thing that is not known is g m plus 1. Because up to gm, everything is solved using em. So gm m plus 1 is the new unknown at order alpha to the 2m plus 2. And the equation of motion would be E m plus 1 evaluated on G m plus 1. But a large part of it is already 0, we have checked, because this is order alpha to the 2m plus 2. Really small time now. Now in this equation, the terms that will contain the unknown, this gm plus 1, are E0, the zeroth order thing, evaluated on G0AB plus alpha to the 2m plus 2 gm plus 1. This is because gm plus 1 already has an alpha to the 2m plus 2. So any term that will have an gm plus 1 will already have an alpha to the 2m plus 2, therefore should not have any other alpha from anywhere. We are calculating the equation at order alpha to the 2m plus 2. So therefore this must be inserted here in E0. E0 doesn't have any alpha, and this has to be linearized. So Einstein tensor linearized around G0AB it's an universal form. G0AB with fluctuations as alpha to the 2m plus 2 gm plus 1 AB will give the differential part of the equation, will give the equation where unknowns are there. Basically the LHS of the equation, unknowns are present. So it's a linear differential equation, so linear PDE. Oh, I'm a bit fast here. Okay, question. And the source term, so that this is the one source of alpha to the 2m plus 2 order term, where this gm plus 1 is there. And the other sources will be this one, the one that we have already tested, the EM evaluated on GMAB at order alpha to the 2m plus 2. These are the parts that were not present there. Therefore, you have to correct it. So the other part
Anthony,
is,
the tau I component will be exactly del I of Cm plus 1. Is that right?
That's the point. Here, this is the only thing. Yeah, this is the only thing I want to say. The tau I component of this thing, the tau I component here also is the same thing. Del I of Cm plus 1. So here the tau I component is again proportional to del I of Cm plus 1. It follows from the zeroth order calculation, some universal form. At every order, it will be like this. And now the source term. So del I of Cm plus 1, I want it to be constant. So the source term has to be constant. So it will have some right-hand side. And this right-hand side will be generated from this kind of a term, from this term, this order alpha to the 2m plus 2 term. So GMAB does not solve EMAB exactly. There's some one more thing. GMAB does not solve EMAB exactly. So it can generate some, it solves only up to order alpha to the 2m plus 2 term. And when we are correct, then that's why we are correcting the metric at order alpha to the 2m plus 2 order. And this metric has to be constructed in a way so that it cancels this alpha to the 2m plus 2 corrections generated in the previous order. So in the end, the equation will look like this. Del I of Cm plus 1 up to term is acting on this Tm on Gm, but calculated up to order alpha to the 2m plus 1 at order alpha to the 2m plus 2. And one more term, which is Em plus 1, which will be actually on C0. At m plus 1 order, there could be new terms in the equation of motion, and that has to be evaluated on G0 because Em plus 1 already has an alpha to the 2m plus 2. So this is the net source term, but we have already assumed that GMAB solves the equation and the temperature is constant for GMAB, temperature is constant for C0. So there C is constant. So in the truncated space, okay, sorry, I'll take just 1 minute. In the truncated space, it's an auxiliary space, let's assume. Yes, auxiliary, which is defined like this. Let's say the XB. In this space, it's not the real space, it's a truncated space, but in this space, the temperature is constant. The zeroth law is true, according to our assumption. It's constant. So we could do the coordinate transformation. So boost symmetry. So we could apply the arguments of boost symmetry. Arguments of boost symmetry. And if I can apply, then I'm looking at E tau I component. Oh, this is E tau I component everywhere. So in the E tau I component, after this boost transformation will become V times E Vi plus minus. If you apply the coordinate transformation here, this is what it will turn out to be ERI in the boost invariant coordinate. And at r equal to 0, this will vanish because there is an explicit Ri. So it will be equal to V times EVI at r equal to 0. And EVI, you see, is a term which has a boost to it V. And the metric, it is being evaluated on GMAB, which is stationary and temperature is constant. So this will vanish using the arguments of boost symmetry. So therefore, E tau I at r equal to 0, because it is of this form, it will vanish. The same is true here. E tau I is a covariant tensor evaluated on GMAB, which is stationary, temperature is constant according to our assumption. Everything is true up to order M. And therefore, E tau I will go to EVI and it will be 0. So therefore, source is 0. So if up to mth order it is true, m plus 1th order, it will again be true because del I Cm plus 1 is true. So this way, perturbatively, we could prove that the C is constant. So this way.
Sayantani, can I just ask one thing? I mean, I haven't followed the details, but the idea that so you are saying that this del I C, I mean, whatever appears on the right hand side has a positive boost to it, and hence it vanishes at r equal to 0. Is that right?
Yes, exactly. That's what I'm saying.
So this quantity on the right hand side has positive boost to it.
It's exactly what I'm saying. Nothing more than that. It has a positive boost to it. And I can apply the argument of boost to it because up to order M, I have assumed that everything is true. It's a method of induction. Up to order M, C is constant. I can apply the argument of boost to it provided C is constant.
Yeah, that's what I'm wondering, because C, I mean, boost to it, I thought was the stationarity assumption, right? But C being constant is not part of that, no? So why do you need constant?
No, she is constant is a stationarity. Like everything, C is constant only in stationarity. Even C is defined in that way.
But C could be a function of Yi and the boost invariance should still be maintained, right?
C could be the functions of Yi and the boost invariance will be maintained. Oh, that is, no, just a minute.
Yes.
Boost invariance is complete boost invariance you are saying in a stationary metric, right?
Yes,
there are
exactly.
2 types of boost invariant. One is this R and dV square is coupling. That will be maintained even if C is not a constant.
Yes.
But in a stationary metric, Z being a function of R times V, That will not be true if C is constant. C is not a constant, because you see this coordinate transformation.
Oh, I see.
In this coordinate transformation, if C is constant, it will generate, not a constant, it will generate a dr dy item.
Okay.
And then to cancel that, I have to redefine y as a function of r. And because it explicitly depends on y, all the r and v dependence will not be through products.
Okay. So form of the metric will change. You can still define v and r this way, and tau translation will induce boost invariance, but the form of the metric will not be the same as what you had written.
It will not be r times b, there will be something different. And the boost invariance is this tau translation symmetry. So if it is there, it must be there in any other coordinate, but the transformation will be much more complicated. And then this vanishing of a tensor, if it is not a function of r times b, then we won't be able to say that it will vanish because it has a positive boost to it on stationarity. Like stationarity, it is vanishing because it's a function of r times v. Every v will pull down a factor of r, and which will vanish at r equal to 0.
I see.
So this way,
why doesn't it trivially generalize when you have matter? Because can't you argue that tau I is also has a positive boost to it, and hence it must vanish?
It's all, I think it is trivially generalized to matter. No particular issue. It's trivially generalized. Only thing I should say I'm not saying it because at zeroth order, everything has to be exact.
Yeah.
Einstein tensor. So zeroth order, if you are having a matter, you will have some tau I component. And then it is said that this T tau I is vanishing because of some dominant energy condition on equilibrium. That energy condition, I don't understand that much. That's why it's well known and very well accepted. So that's why I avoided saying this. T tau I should vanish exactly. And after that, everything will be the same thing. There's nothing else. No difference in matter. And T tau I as second order vanishes is well known. I think it's everywhere it is written that because of dominant energy condition, it is 0 on stationary solution.
Okay,
and if that you accept, then everything will be true. So this is the proof. Proof seems to be so this way. We put automatically. Yes. This proof, I actually, after proving this, we wrote to Harvey Real asking whether it has already been done somewhere or not, because so he told us that it has been done in different contexts for different particular higher derivative theory, but not for all higher derivative theories in this way. But he was saying that it would be interesting. So one of the future direction that he suggested, future direction, without using if it could be generalized to situations, generalizing cases where the solution does not admit a smooth alpha to 0 limit, like the solution. So that's for alpha going to 0 limit. So that is a different form of proof altogether. This one will not be. So this is one of the general future direction that is suggested. And okay, this is it. Okay, I'm done. Thank you.
So are there more questions?
So in your future direction, that means theories which are not perturbatively connected to Einstein-Hilbert gravity.
Theories are perturbatively connected to Einstein-Hilbert gravity, but you are considering solutions which are not perturbatively connected to the solution of Einstein gravity. So solutions are not constructed this way. That's what I think he meant. So alpha is still small. but you are considering a solution where alpha is taken as if a finite thing. Okay, I'm not sure of the physical motivation of that. Okay, that's what I think he suggests.
Are there any solutions known where to higher derivative theories of gravity which do not admit an alpha goes to zero limit?
Like I'm not even, okay, I don't know exactly whether it's known or not.
I've never heard this.
I have just,
Okay, if there are no more questions, let's thank Sayantani for this wonderful talk.
thank you.
Thank you, Sayantani.
Thank you.
If you put alpha to the zero,
maybe hypothetically construct some gravitational solution which is not at all connected.
I think there is some bit of phenomenology involved here. Yeah, that will.
first of all, I'm not sure of this. How important is this coordinate system? Is there a more coherent way of doing this? Just wondering whether one can do this in a more coherent way rather than going to this RP. See, the point is,
I'm sure. I agree. Eight factor kind of thing.